Let's continue our discussions on subRiemannian geometry. Carnot groups, and more generally Carnot-Carathéodory spaces, appear as limiting metric spaces, like limits of metric spaces. They naturally appear both as distinguished asymptotic spaces and as tangent spaces. Mostly, at least for tangents, one can limit the study to distances that converge uniformly on compact sets. But for considering also finitely generated groups, it may be useful to consider convergence as it is formalized by the Gromov-Hausdorff convergence. So in the next videos, we will discuss limits of metric spaces. Let's start. So we are going to discuss limits of metric spaces. And the reason is that Carnot-Carathéodory spaces, and in particular Carnot groups, appear naturally here as limit spaces. Like there are natural spaces in mathematics, and when you take some limits of these spaces, you get Carnot-Carathéodory spaces. So first thing, before presenting these results about appearance of Carnot-Carathéodory spaces, let's clarify what is the meaning of a limit of metric spaces. Okay, so what we have to do, we need to formalize what it means when we have a sequence of metric spaces, so sets with distance functions, and we wanted this as a sequence in I going to infinity converge to a set equipped with a distance. Okay, so these objects here are metric spaces. Okay. First of all, okay, we are in the class of metric spaces, right? And so the first simple remark is that if two metric spaces are isometric, then they should be considered the same, okay? So let's say that two metric spaces are the same if they are isometric. What does it mean? If they are isometric. Okay, what does it mean? This means that x is a function. Let's say that the two metric spaces are x with its distance and y with its distance. If we have a map from x to y that preserves completely the structure of a metric space. So preserves the distance. So if you take 2 points, x and x prime, you look at the image, and then the distance is exactly the distance of the 2 points in x, then this means f is preserving the distance. But of course, f has to be also surjective, right? So this object here tells you that you have an embedding, so continuous, right? And on the image, the inverse is continuous, but what we also want is that f is surjective, and therefore is going to be a homomorphism. Okay, so starting looking at this this trivial notion of isometry, we are going to make it a little bit less rigid. Okay, so we're going to say that two metric spaces are let's be vague for a moment, are quasi the same if, by analogy terminology, if there is a quasi-isometry between them. Okay, what does it mean? It means we have two sets, two metric space, X and Y, and we have a map, F, between X and Y. We said that this is an L, C quasi-isometry. In brief, we'll just say L, C, QI. If, so with, maybe we have to say, we L greater than or equal than 1 and C greater than or equal than 0, if we have the relaxation of the previous condition. So the first one, so now the distance between two image points is not exactly preserved. So it's preserved up to a multiplicative constant. This would be the Lipschitz condition. But we also have an additive constant, C. And likewise, from below, we have 1 over L, the distance of the 2 points. This would be just, without this term, would be the by Lipschitz condition. But now we also have, with a minus here, we have an additive constant, okay? So this should be true for all X and X prime in capital X. So of course, this doesn't say anything about the surjectivity of the map. So the second condition would be that the map is almost surjective. Namely, if you take a point in a point in Y, then maybe there is no X that goes to that point, but the condition is that there exists X for which the distance of the image point that is not too far from Y. Namely, the distance is controlled uniformly in C, with C is the same constant here. And this is the constant of the definition of quasi-isometry. Now, this condition, the first one, is also called quasi-isometric embedding. Okay, so this is an LCQI embedding. And this second one is also called, we will also say that the set f of x, so the image, is a C-net for in Y. Okay, so let's immediately see some examples. All right, so first example, Zn and Rn are quasi-isometric. Really, actually, the map from Zn included in Rn, this gives a quasi-isometry. Let's say that, for example, if on Zn we consider the restriction of the distance from Rn, this map is really a 1C quasi-isometry. A second example is whenever you have a compact metric space, then this metric space is quasi-isometric to the metric space formed by just a single point. So we say it's quasi-isometric to a point. And the map, the quasi-isometry is really the constant map. Okay, so this is this notion of quasi-isometry. Let's go to convergence. Suppose you have a sequence of metric spaces with a choice of base points, and you have another sequence. These are sequences of pointed metric spaces. And let's say that, okay, let's suppose we have maps. When I say maps, I don't really mean that they're continuous, right? Just functions from xj to yj. And writing like this, we mean that with this also, we also mean that that the base point is preserved, so that phi j of xj is equal to yj. So it's preserving the base point. We said that is an Hausdorff approximating sequence if for all r thought as a radius, for all delta, which is thought as an error, there exists a sequence of numbers that going to 0, such that first, okay, phi j restricted to the ball xr, so maybe xjr, this is an 1 epsilon j quasi-isometric embedding. Of course, so from this space to yj. And second, for all y, yeah, maybe I'll make it say that if we have the image of the R ball is j epsilon j net for b yj, and maybe we have to squeeze a little bit. Okay, what does this last statement means? This means that every point in this ball is a distance at most epsilon j from a point in here. Okay, so maybe I'll rewrite it. 2 means for all y in the ball epsilon r minus delta, there exists x in b, so this is maybe I should not have, this is yj ball xjr, and here this balls means that the first ball is a ball in yj, or with respect to the distance dj, and the second ball is in xj, such that the distance between phi j of x and y is less than epsilon j. Okay. We can also write the neighborhood of f b x j r with radius epsilon j contains the ball at y j of radius r minus delta. Okay. Now, the reason why there is this minus delta is because these metric spaces might not be geodesic spaces. If you have geodesic spaces, you can really take delta equal to 0, and it's going to be the same notion. Okay. Let me rephrase once more these two conditions of being Hausdorff approximating an Hausdorff approximating sequence. So rephrasing. For all r and for all delta, First, if I take the limit in j going to infinity of the supremum of the following set, the absolute value of the distance of image points minus the distance of points. So this is for A and B in the ball at yj, no, at xj, with radius r. Then this is equal to, this limit is equal to 0. Okay. The second condition was the limit as j is going to infinity of the supremum of the distance dj from an arbitrary point in y. Let's call it, I can call it y to the set phi j of b xj r minus delta, such that y varies in the ball of radius. Sorry, here I have to put plus. Okay, it doesn't matter if I mean, this set should be bigger than this one, right? So here y is in the ball of center yj and radius r. This limit should be 0. Okay, of course I could put here r and here r minus delta. It's the same, right? As soon as this number is greater than this number, the limit should be 0. This is the second condition for Gromov-Hausdorff approximating sequence. Okay, now, so when we have two sequences of metric spaces and we have this approximating sequence, we should consider them to be closer and closer together. Now, the limit of a metric space will be just a constant sequence and a sequence of Gromov approximating sequence for a sequence of metric spaces. Okay, let's write, well, definition. Suppose we have a sequence of sets with distances, okay? So this is a sequence of metric spaces. We say that they, and we have to choose base points. So let's say that I don't write the distance, but only write the base point. So this is a sequence of pointed metric space. We say that Gromov-Hausdorff converges to a pointed metric space y pointed with y if there exists a Hausdorff approximating sequence let's call it phi j from xj pointed at xj to the pointed metric space y. Namely, now we have a constant sequence of metric space equal to y. Okay? So this is the formalization of this sequence of pointed metric spaces converging to this pointed metric space. Okay. So this is the general definition of Gromov-Hausdorff convergence. Now I will present two criteria to deduce that one has Gromov-Hausdorff convergence. So first criterion. So suppose you have a sequence of metric spaces, pointed metric spaces, and another pointed metric spaces. So these are pointed metric spaces. if one has that for some sequence going to 0, there exist maps Vj from xj, point xj to y that are 1 epsilon j quasi-isometries, then, and you really have, you have convergence in the Gromov-Hausdorff sense. Okay, so this is a sufficient condition. It's not really necessary. So if one has quasi-isometries with the constant 1 and something and it's going to 0, then you have Gromov-Hausdorff convergence. Okay, try to understand why this is true. It's very easy. Just play around with the definitions. Okay. So let's see some examples. So suppose you have xj that are pointed metric spaces of diameter epsilon j, and assume that this epsilon j is converging to 0. Then I claim that this sequence of pointed metric spaces converges Gromov-Hausdorff to a single point. So point, right? So this is the, it's called point P. Right? So this is the metric space, the only metric space up to isometry that has cardinality 1. Okay, it's the metric space with cardinality 1. Okay, so let's fix one, and so fix point P, and we can take the Gromov-Hausdorff approximation to be constantly equal to this point P. So phi j go from xj to this single metric pointed metric space, and let's check that this is a 1 epsilon quasi-isometry. Okay, now let's note that. Okay, so the distance of the image of 2 points, right? So this is just it's 0 because this is these are the same points equal to p, and of course this is going to be less than the distance between x and x prime because it's a positive number, and of course we can even add an error. So this is true. On the other hand, I claim that this is less or equal, so this value is greater than the distance between the point x prime if I remove epsilon j. And this is because by definition of diameter less than epsilon j, then this number is less than epsilon j. So for sure this number is a negative number. Okay, so what we have is that the map phi j are really globally 1 epsilon j quasi-isometric embeddings, and what about the surjectivity? So the image of this map is just a single point P, and if I take the neighborhood, the epsilon j neighborhood, no, that's it. These maps are surjective. Yeah. Okay. So so these are surjective, and therefore we have a 1 epsilon j quasi-isometry. Because of the criterion, we have since these epsilon j are supposed to go to 0, then we have that these metric spaces converge to the pointed metric space. And it's clear what's happening. We have metric spaces that are in scale, they're getting smaller and smaller and smaller, and the limit is just 1 point. Okay. Let's go back to the fact that here there is just one metric space consisting of one point. I mean, this is a more general fact that we are considering equivalent to spaces that are equivalent up to isometries, but this is actually this type of convergence does not distinguish between a metric space and or from its completion. And because of this, I will explain better, but because of this, we shall just restrict to complete metric spaces. We shall restrict to complete metric spaces. Okay, let me see what this note means with an example. So let's consider Q, like the rational numbers. Equipped with the Euclidean distance. Now, the metric completion is going to be the real line, okay? And we see that what's happening is that if we consider the constant sequence, constant sequence Q, then this sequence converges in the definition that we gave, to the Gromov-Hausdorff sense, to R. Okay, so this distance is equal to this one, because the identity is going to be a 1 epsilon quasi-isometry for actually any epsilon. Okay, so this was a side remark. Let's move to a second criterion. And this is when we have distances that are uniformly converging on a fixed set. So the set is going to be the same. And then let's say we have a distance, which is going to be a limiting distance, and these approximation distances. So all of these are distances on the same set X. Let's fix a point, let's call it x0 in X. And let's assume that we can prove that the distance dj, distance maybe some functions, the distance functions converge to D uniformly on sets that are bounded for the distance d infinity. It's called the infinity bounded sets. And two, for all radius r, there exists some d positive, such that the diameter with respect to the distance d infinity of the ball with respect to dj, center x0 radius r, is bounded by d. This is for all j. So in other words, see, balls of radius r are uniformly bounded in respect to the distance d infinity. Okay, one needs to also require this property. Then what we have is that the identity map from x equipped with the distance dj pointed at x0 to x d infinity pointed at x0, this map they form as a family of map in J, is an Hausdorff approximating sequence. And therefore, the metric space distance dj pointed at x0 Gromov-Hausdorff converge to x d infinity, x0. Okay, so check that you understand why this criterion give Gromov-Hausdorff convergence. And this is something that we might use very often. Okay. Now that we know how to take limits of metric spaces, let's talk about asymptotic cones and tangent cones. So asymptotic cones and tangent cones. Okay, so if so let's say if you have, suppose we have a metric space. It's a metric space with distance function. Let's call it d. And we fix a real number lambda, a positive number, positive number lambda. We denote by lambda x the metric space where the set, set-wise, is still the same set x. And the distance function is lambda times d. Okay, it's very easy to check that this is still a distance function. Okay, and now we will see what happens when lambda varies. So there will be two interesting cases. The first one is when lambda j goes to infinity. This is always as it's a sequence going to infinity. And the other case is when lambda j goes to 0. So if this sequence of metric spaces, lambda j x converges, so in the first case, we will say that we're going to have a tangent space. And in the second case, we are going to talk about an asymptote. Okay, I will reformalize better these cases with the definition. But let's see at least one example of what's happening when you dilate the space. Okay. So here's an example. So suppose you have G, a Carnot group with some Carnot-Cartesian distance, fix lambda, or maybe take any lambda, take any Carnot group. Then I claim that this new metric space with the dilated distance, I claim that this is isometric to G itself. Not via the identity, but via the maps, or the map, delta lambda. Why? Okay. So what is happening? So let's recall the property of the map. So if you dilate 2 points, so G and G prime, their distance becomes exactly lambda times the distance of G prime. Okay. So these are distances in G. Okay. But now this last one, lambda G, this is exactly the distance for the metric space delta G. G prime. Okay. So which means that from G to lambda G, the map's delta lambda becomes an isometry. Okay. And therefore, this will tell us that whenever we dilate a Carnot group, we get the same exact metric space. This will tell us that all the tangent space of a Carnot group and all the asymptotic cone of the Carnot group coincide with the Carnot group itself. Okay. Now, in the next video, we will discuss more the notion of tangent spaces and asymptotic cones. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.